let us learn interpretation of vibrational spectra. That is, how we can interpret the IR spectrum. Interpreting a vibrational spectrum involves analyzing the peaks or bands present at specific frequencies to identify the functional groups and bonds within the molecule, essentially acting as a molecular fingerprint to identify unknown compounds or study the structure and dynamics of a known molecule by examining which vibrational modes are active and at what frequencies. This is primarily done using techniques like infrared and Raman spectroscopy. Interpreting a spectrum involves correlating the absorption bands in a spectrum with known absorption frequencies. This process helps to identify the structure of the molecule. Molecules have covalent bonds and have characteristic frequencies. These bonds rotate, bend, stretch continuously. If these bonds are given some energy, that is infrared radiation, they will bend, rotate, or stretch more vigorously, and radiation of that frequency will be absorbed. IR is the most useful in providing the information about the presence or absence of specific functional groups, which is abbreviated as FGR, which will lie in the analytic region, which are very useful. IR can provide a molecular fingerprint that can be used for the identification of samples, FTIR, fingerprint. The key points about interpreting vibrational spectra. Peak position. The location of a peak on the spectrum corresponds to the vibrational frequency of a specific bond or any functional group, which can be used to identify the type of bond. For example, C double bond with O, CH, NH. Intensity. The peak intensity reflects the strength of the dipole moment change during the vibration, meaning stronger dipole moment changes result in more intense peaks. Selection rules. Not all vibrations are IR or Raman active. Due to symmetry considerations, only vibrations that cause a change in the molecule's dipole moment will be observed in IR, while Raman spectroscopy then detects symmetric vibrations. Fingerprint region. In IR spectroscopy, the complex region below 1500 cm⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ Many different vibrational modes overlap, making it useful for identifying the unique molecules. How to interpret a vibrational spectrum? One can compare with a reference spectra. A key step is to compare the observed spectrum to a database of known compounds to identify the potential matches. Assign functional groups. By analyzing the peak positions and intensities, identify the functional groups present in the molecule based on known characteristic vibrational frequencies. Consider molecular symmetry. For complex molecules, understanding the molecule symmetry can help predict which vibration modes will be active in IR or Raman spectra. Use computation methods. Advanced analysis often involves using computational physics software to calculate the vibrational frequencies and compare them to experimental data to confirm assignments. Examples of vibration modes and their typical frequency ranges. So one can observe, see single bond, this is single bond, so CH stretch, and which lies at the high frequency around 3000 per centimeter. OH stretch and this one also lies around 3500 centimeter per minus 1. NH stretch, and this one also lies at high frequency around 3500 centimeter per minus 1. See double bond with O, so CO stretch, its medium frequency around 1700 centimeter per minus 1. CC stretch, double bond, medium frequency around 1600 per centimeter. CN stretch, medium frequency, which lies at 1100 per centimeter. At least we should, out of 6 stretches, at least we should know 4 stretches by heart. We'll learn one by one. So spectral requirements. The spectrum must be adequately resolved and adequate intensity. The spectrum should be a pure compound. The spectrophotometer should be calibrated so that the bands are observed at their proper frequencies or wavelength. The method of sample handling must be specified. If a solvent is employed, the solvent concentration and the cell thickness should be identified. We know that all bonds in the molecules vibrate. If it vibrates, it's going to be visible in the infrared region. If we shine the IR radiation on the molecules, different functional groups observe the different frequencies of IR light. Hence, one can confirm that the names of the compounds inside the molecule. Whenever we look into IR spectrum, there are 2 regions. One is fingerprint region, which is less than 1500 per centimeter, and another one is analytical region, which lies between 4000 and 1500 per centimeter. But we are going to analyze all the compounds in the molecule in the analytic region, whereas the fingerprint region is useful if you are going to identify our molecule by comparing with a known sample. The molecule in the fingerprint region is unique for each molecule. We are going to obtain the wave number which is related to the vibration frequency and directly proportional to the energy of the molecule at which the bonds are vibrating. Higher the wave number, higher the energy of the molecule which the bond vibrates. The different types of bands can be explained as follows. If the signal peak dips down with 30% of transmittance, it means the signal is strong. If the peak is at the middle, then the signal is medium. If the signal is weak, if the peak is higher than 30% of the transmittance. This is as shown in the figure. So you have in the y-axis, you have percentage of transmission, and this is a weak absorption, weak transmission, and this will be considered as medium transmission, and this will be strong transmission. See, this is a strong transmission, and this is around 30%, and this will be around 30 to 60%, and this will be around 60 to 100%. Once if we know the wave number and the shape, which is nothing but smooth or spike, we can match it with a reference table. Here is the reference figure in the next slide, and the table with 4 functional groups. As I said earlier, we need to learn by heart at least 4 functional groups. We should start from left to right. So we are going to start from the chart or reference table or reference figure from left to right. In general, the IR spectrum can be split into 4 regions for interpretation. So minimum 4 regions we have to learn by heart. At least we should know. So the first region lies between 4000 and 2500 per centimeter. That is absorption of single bonds formed by hydrogen and other elements. That is OH or NH or CH functional groups. 2500 and 2000 per centimeter absorption of triple bonds. Either it can be CC or CN bonds. 2500 to 1500 per centimeter absorption of double bonds. That is, it can be CC or CO double bonds. 1500 to 400 per centimeter, this region often consists of many different complicated bands. This part of the spectrum is unique to each compound and is often called as fingerprint region. It is rarely used for identification of particular functional groups. So as I said earlier, minimum 4 types we have to learn, minimum 4. So this is the highest wave number, and this region lies between 2500 and 2000, and double bond, CC double bond, CO double bond, CN double bond, that lies between this region 1800 and 1600 per centimeter, and fingerprint region which we don't know. So we need to have the knowledge of this region and this region and this region. The typical IR absorption range for covalent bonds is 600 to 4000 per centimeter. The graph shows the regions of spectrum where the following types of bonds normally absorb. For example, sharp band is around, which lies between 2200 and 2400 per centimeter, would indicate the possible presence of CN or CC triple bonds. So C triple bonds, CC or CN triple bonds. This, if the wave number lies between 2200 and 2400 per centimeter. And this is a typical IR spectrum, so which we can obtain from the lab, and look at the region, and this is so 3500 and this is 2500, and look at the range. This is 2500 and this is 2000. This is 3500 and this must be 2500. And OH touching, NH touching, CH touching will lie only within this region. And all triple bonds, especially CC triple bonds and CN triple bonds, they lie in this region. And double bonds, CC, CO and CN, they lie between this region. And this is your fingerprint, which we don't want. Either we can look at the earlier reference figure, or we can have the correlation shortened table. So here it is given as 8 things are there, but at least we need to learn 4. So OH stretching lies at the wave number 3400 per centimeter. NH also lies at the 3400. How to differentiate these two? By means of sharpness and smoothness, one can differentiate one. And second one is either it should be strong or it should be weak. So we can differentiate these two. So here you have OH and NH stretching. We have these two numbers are the same. How to differentiate? Only by means of either sharpness or by means of smoothness. And otherwise, strong, weak, medium, one can differentiate. And CH stretching, single bond CH stretching lies at 3000 per centimeter. Triple bond, CN triple bond lies at 2250 per centimeter. And triple bond, CC triple bonds lies at the wave number 2150 per centimeter. Double bond, CO. So it lies 1715 per centimeter, and here we have double bonds again, C double bond. So 1650 per centimeter, and single bond, CO single bond, which lies at 1100 per centimeter. And this is the Fourier Transform Infrared Spectroscopy, see here. And in this region, as I said earlier, around 4000 to 3500, both will occur, either OH or NH. But whereas, how to differentiate these two, as I said, so NH is weak it's sharp, whereas OH is strong and smooth. So we are going to differentiate by means of getting the signals. So if it is strong in the same region, we can say that this is OH, OH bond, OH functional group. And if it is very sharp and weak, this is NH functional group. And of course, this is very, very strong at 3000 per centimeter. So CH strong. And what is this triple bond? CN triple bond and CC triple bond. The wave number lies between 2500 and 2000. We can say that this is weak. So CN and CC are weak signals. And of course, CO stretching is very strong. See, very strong. And it lies between 2000 and 1500. And of course, less than 1500, we say this is fingerprint, which we don't want. So as I said earlier, at minimum 4 regions we need to learn. So this is a typical infrared absorption region, minimum 4 regions. So we can learn 1, 2, 3, 4. And of course, the last one is fingerprint, which we don't know. So minimum 4 signals we should know. And also the corresponding ranges. So now, for example, when you take, as I said earlier, this is a typical IR spectrum. So look at this signal. This signal lies at 3420.23 per centimeter. And what is this NH? Yeah, this is NH touching. And OH and NH both lie between 3500 and 3000 per centimeter. How to differentiate these two? See, OH lies very smooth here, very smooth and broad, whereas NH touching is weak and also it's very sharper. See, very sharp, it's sharp. And what about these two? So look at the signals. The left hand side of 3000 per centimeter is sp2 hybridization, CH bond, CH bond. Whereas right hand side of wave 3000 wave number per centimeter, and this is sp3 hybridization of CH bonds. So one should differentiate. And of course, as I said earlier, if the percentage transmission lies up to 30, it is very strong signal. And from 30 to 60, it is medium. And 60 to 100, it is weak. The area around 3500 per centimeter belongs to OH and NS groups. The broad and smooth curve represent OH group. So this is out of the figure that we have learned. Whereas NH group will be weak and sharpened. Out of the shapes one can differentiate. So now carbon-hydrogen bonds. Bonds with more S character absorb at a higher frequency. sp3 alkane. CH just below 3000 per centimeter to the right. sp2 hybridization alkene or aromatic hydrocarbon. CH just above 3000 centimeter, that is to the left. So sp alkane, this is CH at 3300 per centimeter. If CO is absent, alcohols and phenols, one should check for OH stretch, and it shows broad absorption near 3400 to 3300 per centimeter. Confirm this by finding CO bending near 1300 to 1000 per centimeter. Amines, there will be NH stretch, and it will show medium absorption near 3400 per centimeter. Ethers, there will be CO bending near 1300 to 1000 per centimeter, and also it will be the absence of OH near 3400 per centimeter. The fingerprint region. Although the entire IR spectrum can be used as a fingerprint for the purposes of comparing molecules, that is, the range lies between 600 and 1400 per centimeter, is called as fingerprint region. This complexity limits its use to that of a fingerprint and should be ignored by beginners when analyzing the spectrum. That is, the region at the rate of 1400 per centimeter. Carbon-carbon bonds. Increasing bond order leads to the higher frequencies. Single bond CC setting, which lies at 1200 per centimeter, which is nothing but fingerprint region, which we don't want. See double bond, CC double bond, which is observed between 1600 and 1680 per centimeter. See double bond, which is very weak, absent if internal, which lies at the wave number 2200 per centimeter. Conjugation lowers the frequency. Isolated C double bonds lies between these two regions, 1640 and 1680 per centimeter. Conjugated double bond CC double bond lies between 1620 and 1640 per centimeter. Aromatic C double bond approximately lies at 1600 per centimeter. C double bond with C peaks are generally weak to moderate in intensity. And so you just look at the IR spectrum. In the y-axis is percentage transmittance and the x-axis wave number per centimeter. And this is a CH, see CH. And as I said earlier, that 3000. To the left and right, we have two peaks. One is sp2 hybridization, another one is sp3 hybridization. So here it is CH, such, this one. So this is sp hybridization with the CH triple bond. So this one. And triple bond lives in the region between 2500 and 2000 centimeter. So this is nothing but your C triple bond. And what is this? So this bond is 1893 per centimeter it lies. So this is C double bond with C, CC double bond. The double bond lives between the region 1800 and 1500 per centimeter. CO is at 1963. So this is CO, this is 1963 per centimeter, and CC is 1041 per centimeter. These are the most prominent functional groups in this molecule. See, we have three bonds. One is CO, another one is CC. See here we have two bonds here, CO and CC. CO here and this is CC. We'll find out the example one, and we'll find out what is the molecule about. And here there is no signal here. See, the y-axis has, as it is given as percentage of transmittance against wave number, and there is no signal here between the region 3500 and 3000. So there will be no NH or OH groups. Here there is no. And what are this? The one spike is here. So there are spikes at the right side of 3000. So it must be sp3 hybridization with the CH structure. Suppose if there is one spike at the left side, this is sp2 hybridization CH structure. But here it is sp3 hybridization with the CH structure. And what are this peak? This peak refers, that is at 1716 per centimeter. It is CO bending. See, this is CO bending structure. See, double bond with O. So this must be maybe keto. Okay. And this is a detailed spectrum of IR molecule, as we discussed earlier. And see, around 3500, we have two very important structures. One is OH and NH. So this is a single bond structure, and this is about CH structure, which lies between, which lies around the 3000. But one to be left, another is right, sp3 and sp2. And next one is triple bond, nitrates and carbonyls, and this one is double bond, which is very important, CO, CC, CN. So they are all double bonds and bending structures. And this one also fingerprint. This will go with the fingerprint. Now we will find out the spectra of alcohol. So alcohols, example is nothing but ethanol, and functional group is nothing but OH. So we have CH3, CH2, OH. The functional group is nothing but OH here. So we'll find out first OH stretching. See, at the figure we have A refers OH stretching. So this is observed at 3330 per centimeter. See here, this one is OH stretch. What is the next one? B, at the point B. This is the CH stretching in CH3. So we have CH3, we have CH stretching. And similarly, we have CH in CH2 stretching. And this lies at 2954 per centimeter. Then the next bond will be CO stretching between these two. So CO stretching. So which is observed at D equals 1050 per centimeter. Thus we have 4 peaks in the amine functional groups. Now we'll go for amines. And this is CH3, CH2, CH2, NH2. So we have one more, I have written one more CH2. So there's a mistake here. It's correct. Okay, no problem. CH3, CH2, 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 NH2. Betonomine. The functional group is your NH2. And this is about the spectra of amines. So we have, in CH3 we have CH function. See, this is CH stretch is there, which lies at 2960 per centimeter. And this is CH stretches. In CH2, this is CH2, which lies at 2860 per centimeter, and we have NH stretch, and of course this is the highest wave number observed, so which lies at the point A, 3500 to 3200 per centimeter, and this is a CN stretching, which is the lowest one, which is observed at D equals 1230 to 1030 per centimeter. Thus we have 4 peaks in the amine functional group. Now we'll look at carbonyl compounds. And here the functional group is nothing but CHO. Example is nothing but butanol. So this is about the aldehydes. And the stretching. The first one is CH stretching in CH3. So we have in CH3 we observe CH stretching, which lies at 2972. See A, at the point A we have 2972 per centimeter. And we observe another stretching CH in CH2, that is which lies at B, which is located here in the graph. So which is 2860 per centimeter. And next one is CO stretching. So this is we have CO stretching, which lies at this point D, which is equal to 1740 to 1720 per centimeter. And the last one is CH stretching, and this is located as C, and which lies at 2650 per centimeter. And ketones we have taken the example as ethyl methyl ketone. So we have now CH stretching in CH3 and CH stretching in CH2 here, and of course we have C double bond, CO double bond, and this is CC. So CC stretching, and CH stretching in CH3 lies at 2960 per centimeter, which is located here in the figure. And of course CH stretching in CH2, which lies at the point B at 2860 per centimeter. And double bond, CO double bond structures, which lies at C lies between 1725 and 1705 per centimeter. This is referred as C here. And we have last one is CC single bond structures, and which lies at 1500 per centimeter. Information obtained from IR spectrum. IR is useful in providing information about the presence or absence of specific functional groups. IR can provide a molecular fingerprint that can be used when comparing the samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. IR does not provide detailed information or proof of molecular formula or structure. It provides information on molecular fragments, specifically functional groups. Therefore, it is very limited in scope and must be used in conjunction with other techniques to provide more complete picture of the molecular structure. For example, NMR and other techniques. Features of an IR spectrum. IR spectrum is an absorption, which is another band spectrum. The spectrum is measured between percentage of transmittance and wave number. The wave number represents frequency of IR absorption. Two regions of absorption. One is the analytic one, another one is fingerprint region. So which lies between 4000 and 1500 per centimeter. So this is analytic region to identify the groups, functional groups, and fingerprint region lies between 1500 and 400 per centimeter. So this is fingerprint region. So spectral matching, unknown compounds. Nature, intensity and shape of spectral bands. So one can differentiate strong, medium and weak bonds. In conclusion, one can interpret the IR spectra by comparing the spectrum of an unknown compound with a reference spectrum to identify it, using a frequency table to identify the functional groups for each frequency, considering the bond length, that is short, strong bonds, vibrate at higher frequency than long, weak bonds. However, the IR spectrum will be the first step in the spectroscopic determination of compounds. One can have a complete structure for any compound with a combination of IR, NMR and some other techniques.